4.5 Amplitude modulations, vestigial. Sideband, VSB. Figure 4.20. Spectra of the modulating signal and corresponding DSB, SSB, and VSB signals. As discussed earlier, it is rather difficult to generate exact SSB signals. They generally require that the message signal M, T, have a null around a phase shifter, required in the phase shift method, is unrealizable, or only approximately realizable. The generation of DSB signals is much simpler, but it requires twice the signal bandwidth. Vestigial sideband, VSB, modulation, also called the asymmetric sideband system, is a compromise between DSB and SSB. It inherits the advantages of DSB and SSB but avoids their disadvantages at a small cost. VSB signals are relatively easy to generate, and, at the same time, their bandwidth is only a little, typically 25%, greater than that of SSB signals. In VSB, instead of rejecting one sideband completely, as in SSB, a gradual cutoff of one sideband as shown in Fig. 4.20d, is accepted. The baseband signal can be recovered exactly by a synchronous detector in conjunction with an appropriate equalizer filter H0, F, at the receiver. Output, Fig. 4.21. If a large carrier is transmitted along with the VSB signal, the baseband signal can be recovered by an envelope, or a rectifier, detector. A. F. LOSBU. B. DSB. J. Li. LSSBU. C. SSB. J. FC. LVSBU. D. VSB. FC 168 amplitude modulations and demodulations. Figure 4.21. VSB modulator and demodulator. If the vestigial shaping filter that produces VSB from DSB is H, F, Fig. 4.21, then the resulting VSB signal spectrum is TVSB, equals M, F plus JC, plus MU, JC, H, F, 4.23. This VSB shaping filter H, F, allows the transmission of one sideband but suppresses the other sideband, not completely, but gradually. This makes it easy to realize such a filter, but the transmission bandwidth is now somewhat higher than that of the SSB, where the other sideband is suppressed completely. The bandwidth of the VSB signal is typically 25 to 33%, higher than that of the SSB signals. We require that M, T, be recoverable from QVSB, T, by using synchronous demodulation at the receiver. This is done by multiplying the incoming VSB signal CF VSB, T, by 2 cos WCF. The product E, T, is given by E, T, equals 2 CP VSB, T, cos wet. The signal E, T, is further passed through the low-pass equalizer filter of the transfer function H0, F. The output of the equalizer filter is required to be M, T. Hence, the output signal spectrum is given by M, F, equals VSB, plus J, comma, plus VSB UJC, HO U. Substituting EQ 4.23 into this equation and eliminating the spectra at plus or minus 4 JC suppressed by a low-pass filter H0, F, we obtain. Hence, M, F, equals M, F, H, F plus JC, plus H, F, FC. Ho, F. Ho, slash, equals. H, F plus JC, plus H, F, JC, LFL equals colon, B. 4.24. 4.25. Note that because HF is a band-pass filter, the terms H, F plus or minus JC contain low-pass components. Complementary VSB filter and envelope detection of VSB plus C signals. As a special case of a filter at the VSB modulator, we can choose H, F, such that LFL colon, B, 4.26. The output filter is just a simple low-pass filter with transfer function. M, T. Ho, slash, equals 1. PVSS, T. X1HF, dash. Transmitter. PVSS, T, E, T, M, T. Low pass. Dash plus dash I. Filter Ho, F. Receiver 4.5 amplitude modulations, vestigial sideband, VSB, 169. The resulting VSB signal plus carrier, VSB plus C, can be envelope detected. This demodulation method may be proved by using exactly the same argument used in proving the case for SSB plus C signals. In particular, because of EQ 4.26, we can define a new low-pass filter. F equals JL, 2HF, JC, equals JL, 2 high, F plus JC, LFL colon, B. Defining a new, complex, low-pass signal as MV, T, equals MV, F, equals F, F, M, F. We can rewrite the VSB signal as PVSB, J, equals M, F, JC, plus M, F plus JC, plus MV, F, JC, MV, F plus JC. 221. Equals. PVSB, T, equals M, T, cos 2 NJCT plus MV, T, sin 2 NJCT. 4.27a. 4.27b. Clearly, both the SSB and the VSB modulated signals have the same form, with MH, T, in SSB replaced by a low-pass signal MV, T, in VSB. Applying the same analysis from SSB plus C. Envelope detection, a large carrier addition to VSB plus C. We have shown that SSB plus C requires a much larger carrier than DSB plus C, AM, for enveloping detection. Because VSB plus C is an in-between case, the added carrier required in VSB is larger than that in AM, but smaller than that in SSB plus C. Example 4.7 The carrier frequency of a certain VSB signal is JC equals 20 kHz, nth baseband signal bandwidth is 6 kHz. The VSB shaping filter H, F, at the input, which cuts off the lower sideband gradually over 2 kHz, is shown in Fig. 4.22a. Find the output filter H0, F, required for distortionless reception. Figure 4.22b shows the low-pass segments of H, F plus FC, plus H, FJC, we are interested. In this spectrum only over the baseband, the remaining undesired portion is suppressed by the output filter. This spectrum, which is 0.5 over the band of 0 to 2 kHz, is I from 2 to 6 kHz, as shown in Fig. 4.22b. Figure 4.22c shows the desired output filter H0, F, which is the reciprocal of the spectrum in Fig. 4.22b CEQ. 4.25. Use of VSB in broadcast television. VSB is a clever compromise between SSB and DSB, which makes it very attractive for television broadcast systems. The baseband video signal of television occupies an enormous bandwidth of 4.5 MHz, and a DSB signal needs a bandwidth of 9 MHz. It would seem desirable to use SSB to conserve bandwidth. Unfortunately, doing this creates several problems. First, the baseband video signal has sizable power in the low-frequency region, and consequently it is difficult to suppress one sideband completely. Second, for a broadcast receiver, an envelope detector is preferred over a synchronous one to reduce the receiver cost. We saw earlier that SSB plus C has a very low power efficiency. Moreover, using SSB will increase the receiver cost. The spectral shaping of television VSB signals can be illustrated by Fig. 4.23. The vestigial spectrum is controlled by two filters, the transmitter RF filter HR, F, and the receiver RF filter 170 amplitude modulations and demodulations. Figure 4.22. VSB modulator and receiver filters. Figure 4.23. Transmitter filter. HR.F, receiver. Front end filter. HR.F, and the receiver output. Low pass filter. H0.F, in VSB. Television systems. M.T. -26 -22. T. -18. 2 cos-wet transmitter. HR, F. Jointly we have 0. A. HF. 1. 0.5. B. T. Receiver. High, F, equals HT, F, HRU. 18, 22. FC equals 20 kHz. Hence, the design of the receiver output filter H0, F, follows EQ. 4.25. 26. F kHz. F kHz. F kHz. The DSB spectrum of a television signal is shown in Fig. 4.24a. The vestigial shaping. Filter H, F, cuts off the lower sideband spectrum gradually, starting at 0.75 MHz to 1.25 MHz. Below the carrier frequency JC, as shown in Fig. 4.24b. The receiver output filter H0, F, is designed according to EQ. 4.25. The resulting VSB spectrum bandwidth is 6 MHz. Compare this with the DSB bandwidth of 9 MHz and the SSB bandwidth of 4.5 MHz.